All right. All right. So, today we'll be looking at chapter 13. I don't, oh, somebody actually. Oh, okay. So, unfortunately, I've left my grade book at home. So basically, I'm not taking attendance right now, excepting for the only person in the classroom right now signing the sheet. So there's a signing sheet for them to sign it. So for you guys out there, don't worry, because I'm able to retrieve who attended this class via Zoom. So I'll have a record of you attending this class. So that's an answer to the question or to the statement made by Caden Fitzsimmons. All right. Okay, so we're going to look at chapter 13. I don't remember if I told you guys, but just in case you're wondering, we did chapter 10 the last time, and in my opinion, chapter 13, the topics covered in chapter 13 is a natural follow-on topic from what we learned in chapter 10. So that's the reason why we have jumped from chapter 10 to 13. And then next week, which will be the final week of lecture, I'm going to do chapter 11. Not sure if we can get to chapter 12, but we'll see how that will work. All right. In fact, I think what I'm going to do is post the videos for both chapters 11 and 12 so that you guys can watch them, and then we can see what we can accomplish next class, which is after break. All right. So let me talk about chapter 13. And again, I'm assuming that you would have watched the videos for that chapter, which deal with gases, right? And in particular, the gas laws which govern the behavior of gases, right? And I'm quite sure we're all familiar with the characteristic of gases, especially if you have watched the videos. Gases, unlike liquids and solids, they have particular properties in that they flow very easily, which it does have in common with liquids, but the difference between gases and liquids is that gases tend to expand to occupy the entire container that they're in. Liquids do not do that, all right? And as a result, well, based on that observation, the kinetic molecular theory was developed. I won't go into it right now because that was also covered in the videos, but basically that theory is used to explain why gases behave the way they do, all right? And basically what the theory says is that the particles of a gas are very energetic, always moving, bumping into each other and bumping into the walls of the container. And as a result of that understanding, we have the gas laws, which basically can be explained. All the gas laws that we're about to discuss can be explained based on the kinetic molecular theory, right? So what I'm going to do, especially in the interest of time, is proceed to look at the problems in assignment number 30. Now, let me just check to see if I have published assignment number 13 for you guys out there in Zoom. Let me see. Yes, I have. Okay, so you guys out there in Zoom, you should be able to retrieve assignment 13. And for you who's inside here, let me give you a copy of that assignment. Oh, cool. Okay, good. All right, so let me put this here just in case some of the students walk in. Okay, so let's look at the questions, starting with the Boy's Law question. So let me, okay, what did I get back? What am I doing? Okay, let's see. Here, okay. So Boy's Law, let me explain what Boy's Law says. Boy's Law is the law which relates the pressure of a gas to its volume. And basically, I can, okay, what's going on? Okay, so Boy's Law relates the pressure of a gas to its volume. And there are several ways of expressing Boy's Law. it can be expressed in words. And I think I've covered that in the videos. Basically, what Boyle's law says is that the pressure of a gas is inversely proportional to its volume, as long as the temperature and the amount of gas is fixed. So mathematically speaking, we can express it this way. P is directly proportional to 1 over V, provided that the number of moles, which is the amount of gas, and the temperature are constant. All right, so this is one way of expressing Boyle's law. Another way of expressing it is P is equal to K times 1 over V, where K is a constant, which again depends on the fact that the number of moles and the temperature is constant, which means that we can rearrange this equation. I'm going to write it over here to get PV is equal to a constant, right? So basically what this form is saying is that when you multiply the pressure of a gas by its volume, that would be equal to a constant. And in my general chemistry 1 lab, and if there are students here who plan to do chemistry 1 with me, then you're going to actually get to see one experiment where this is actually shown to be true, where the product of the pressure and the volume of a gas will be equal to a constant, right? And then there's yet another way of expressing Boyle's law, which is useful for the problem that we're going to look at here, and that is P1 V1 is equal to P2 V2. So basically P1 and V1 would be the initial values of pressure and volume, and P2 and V2 would be the final values of the pressure and volume of a gas. So basically what this equation is all about is that let's say you have a gas where the pressure is of a particular value P1 and the volume is V1, and then you change the pressure of the same gas to V2, then the volume would be adjusted to V2, all right? So that's basically what Boyle's law is saying, and as I said before, this form of the law is going to be useful for solving the problems in this particular assignment. For example, if you look at question number 1, it says, if I have 5.6 liters of gas in a piston at a pressure of 1.5 atmospheres and compress the gas until its volume is 4.8 liters, what will the new pressure inside the piston be? Now, whenever you're given a problem like this, it's very important that you interpret the information given in light of the law that you're going to use. Let me just scroll this down a bit. So just to remind you, the law that you're going to use is P1 V1 is equal to P2 V2. All right. Now, so, and this is where students tend to, slip up, make mistakes and so on. They use the wrong values in the wrong place in this equation. So the way I would interpret this is it says if I have 5.6 liters, so I would interpret this to be V1, right? 5.6 liters, V1, at a pressure of 1.5 atmospheres. So that would be P1, right? And then the question goes on to say, and compress the gas until its volume is 4.8 liters. So that would be V2, right? And the question is asking now, what will the new pressure be? That would be P2, right? So basically you're given V1, V2, and P1, and therefore you can rearrange this equation like this to find, P2. So P2 will be equal to P1, V1 over P2. And then all you have to do is put the numbers in. So P1 is 1.5 atmospheres, V1 is 5.6 liters, divided by V2, which is 4.8 liters, and then we do the number crunching. So 1.5 times 5.6 divided by 4.8, and according to my calculation, when rounded out to 2 sig figs, the final answer becomes 1.8 atmospheres. 1.8 atmospheres, right? The liters unit will cancel out, and therefore that would be the final answer. All right. Now, before we move on to, well, first, let me ask, are there any questions concerning what I've just done? Any questions? Any questions out there in Zoom? Any questions? Okay, now, before we move on to the next question, one thing I want to point out about the use of this equation is that it doesn't matter what the units of pressure for P1 and P2 are, as long as they're the same, right? And the same is true for volume, V1 and V2. It doesn't matter what the units are, as long as V1 units are the same as V2 units, right? So it doesn't matter if P1 and P2 are expressed in atmospheres, or in millimeters mercury, or whatever the pressure unit is, pounds per square inch. As long as they're the same on both sides, then you can put the numbers in and you should get your solution. And the same is true for V1 and V2. It doesn't matter if V1 and V2 are in liters or gallons or milliliters, as long as they're the same on both sides, all right? I should say something here which was covered in the videos concerning pressure. There are several units of pressure that you will encounter in this course. One of them is the atmosphere, right? And the relationship between the atmosphere and other units. Let me just write them down here. I covered these already in the videos, but I think I'll just do that here. There's another unit known as millimeters mercury, right? And the relationship between the atmosphere unit and millimeters mercury is 760 millimeters mercury, right? And there's another unit known as torr, and that is the relationship between the atmosphere unit and torr is 760 torr is equal to 1 atmosphere. So obviously, the torr unit and the millimeter mercury unit are both the same in terms of being equal. There's another unit known as a Pascal unit. Let me see if I can squeeze this in right here. So 1 atmosphere is equal to 101.325 pascals, all right? Or 101.325 kilopascals, all right? You don't need to memorize all these because these are all available in the tables, right? But I just thought I should let you know about those different units. Is there another one? I think that's clear. You can just work it toward. I don't remember if the handout gives you the relationship between atmospheres and pounds per square inch, but I won't go into that right now. So these are pretty much most, if not all, the units of pressure that you will encounter in this chapter, all right? Okay, so if there are no questions about this, let me clear all this here and scroll down to question number 2, which says, a gas occupies 12.3 liters at a pressure of 40.0 millimeters mercury. What is the volume when the pressure is increased to 60.0 millimeters mercury? So again, you'll be using the same equation, P1, V1 is equal to P2, V2. All right, so let me ask you this. What is P1 according to the question here?
40 millimeters mercury.
Exactly, so P1 would be 40 millimeters mercury. What is V1?
12.3 liters.
Exactly. And what is P2?
60 millimeters.
Exactly, so this is P2, and the question is asking for V2, right? So therefore, from this equation, we can rearrange to get V2 is equal to P1, V1 over P2. And then we plug the numbers in. So 40.0 millimeters mercury is P1 multiplied by 12.3 liters, all divided by P2, which is 60.0 millimeters mercury. And again, we do the number crunching. So 40 times 12.3 divided by 60. And according to, I can't correct it, do this thing. 40 times 12.3 divided by 60. Okay, I got, oh, that's correct. Okay, so I got 8.20 liters. We have to round up 3 sig figs because that's 3 sig figs, that is 3 sig figs, and that's 3 sig figs. So the final answer has to be expressed to 3 sig figs. All right. Okay, any question about this? Any questions? Any questions? All right, so if it's okay, Dayu, let me clear this. Let's go down. Okay, so the next question says, if a gas at 25 degrees Celsius occupies 3.60 liters at a pressure of 1.00, well, that's a typo, that should be atmospheres, what will be its volume at a pressure of 2.50 atmospheres? So this should be atmospheres here. It's a typo, all right? Okay, so how would you tackle this problem? Again, the equation is P1. P1 is equal to P2, V2. All right? So how would you tackle this problem?
So V1's gonna be 3.6 liters.
Okay, so this is V1, 3.6.
P1 is 1.00 atmospheres.
Okay,
We're looking for V2 and P2 is 2.5 atmospheres.
okay, very good. So what the question is asking for is V2. And you notice they threw in a 25 degrees Celsius, that's just to throw you off, it has nothing to do with the question, right? Okay, so basically V2 is what we're trying to find. So V2 will be equal to P1, V1 over P2. P1 over P2. And then we plug the numbers in. So P1 is 1.00 atmospheres multiplied by V1, which is 3.60 liters, divided by P2, which is 2.50 atmospheres. So let me see what that gives. So that's basically 3.6 divided by 2.5. So I got, and please correct me if I'm wrong, but I got 1.44, and the units would be liters because the atmosphere units will cancel. All right? Okay, any questions about that one? Any questions? Any questions? All right, let me clear this one. And then you scroll down to the next question. Okay, so this question says, to what pressure must a gas be compressed in order to get into a 3.00 cubic foot tank? Let me see. The entire weight of a gas that occupies, what pressure must a gas be compressed in order to get? Okay, I'm not sure about the weight part of this question, but basically, from what I can, okay. Let me just say that there's a missing piece of information from this question here. It's not really missing, but at this juncture, I wouldn't expect you to know what standard pressure is. But that is discussed later in the video, actually. The standard pressure, let me just include that information here. Standard pressure is equal to 1.00 atmospheres, all right? Later on, we'll talk about what we call STP conditions, standard pressure and temperature. But for now, just accept that standard pressure is 1.00 atmospheres, right? Okay, so based on this information here and the rest of the information in this question, again, it's P1 V1 is equal to P2 V2. That's the equation we're working with. So let's see, how would you tackle this particular problem? What's the question asking for? Let me ask you that first. You sure about that? It says, to what pressure must a gas be compressed? Right? So that's not P1, that would be the new pressure after compression, right? So this is P2, actually, what the question is asking for, all right? What would be P1?
P1 would be standard pressure.
Exactly. So this is P1 right here, okay. What would be V1?
cube.
Exactly, 400.0 cubic feet, so that's V1, which means that the 3.00 cubic feet would be V2, all right? So to get P2, that would be equal to P1 V1 over V2, and then we put the numbers in. So P1 is 1.00 atmospheres multiplied by V1, which is 400.0 feet cube, which is the same thing as cubic feet, divided by V2, which is 3.00 feet cube. And then we do the number crunching. See here, so that's 400 divided by 3. So according to my calculation, round it up to 3 sig figs, that's going to be 1.33, and the units here would be atmospheres. All right? And that's how that is done. Okay? Okay, any questions about this one? Any questions? Okay, what about number 5? We clear this here. Scroll up. or scroll down, I should say. Okay, number 5, it says a gas occupies 1.56 liters at 1.00 atmospheres. What would be the volume of this? And again, there's another typo here. Gas, if the pressure becomes 3.00 atmosphere. Okay, so what's the question asking for? Let me ask you that first.
B2.
P2. Oh, I'm sorry,
No,
P2.
B2.
Yeah, you're right, P2. So what is P1?
1.0 atmospheres,
And V1 is,
1.56 liters.
and of course, P2 would be
30
3
atmospheres.
right, exactly. So we're trying to find V2, which is P1, V1 over P2, and then we plug the numbers in. So P1 is 1.00 atmospheres, multiplied by V1, which is 1.56 liters, all divided by P2, which is 3.00 atmospheres. So let's see what that gives. So that's basically 1.56 divided by 3. So according to my calculation, and again, we have to round off to 3 sig figs, I got 0.520 liters. That's how that is done. Right? Okay. Any questions about this? Any questions? Any questions? Okay, so let me scroll down. Okay, I'm gonna leave number 6 for you to do. I mean, number 6 is basically along the same vein as what we did before. So you should be able to handle that. What I'm gonna do now is look at number 1 under the Charles law section. So let me explain what Charles law says. Charles law is relating the volume of a gas to its temperature, right? And basically what this law says is that V1 over T1 is equal to V2 over T2, all right? There are other ways of expressing it, but this is the way that, this is the equation that we're gonna use to solve the problem. Now, one particular thing you need to pay attention to when it comes to Charles law is that the temperature in this law must, and let me underline that because that's very important, must be expressed in Kelvin. All right. Now, if you remember the relation, I don't remember if I told you this, but in the previous chapter, but I'm quite sure it was covered in this chapter. The relationship between the Kelvin unit and the Celsius unit is this. Temperature in Kelvin, TK, is equal to the temperature in Celsius plus 273, right? So basically, this is the equation which allows you to convert from Celsius to Kelvin. So whatever the Celsius value is, you add it to 273 to get the corresponding Kelvin value, all right? So whenever you're using Charles law, and for that matter, any law that involves temperature, any gas laws that involve temperatures, you have to convert it to Kelvin if you're given the temperature in Celsius, all right? And that is, of course, no less true for this question, because this question says, the temperature inside my refrigerator is about 4 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius and a volume of 0.50 liters, what will be the volume of the balloon when it is fully cooled by my refrigerator, right? So in this question, you have to identify again in different terms. So basically, the 0.50 liters would be the V1 in the equation. The 22 degrees Celsius, which is the initial temperature, would be the T1, but you have to convert that to Kelvin. So basically you have to add 273 plus 22 degrees, and that gives you 295 Kelvin. And 4 degrees Celsius, again, you have to convert to Kelvin. That would be T2. So 273 plus 4 degrees Celsius will give you 277 Kelvin, all right? So the question is asking for V2, right? So basically, to get from here to get to an expression of V2, V2 would be equal to V1 divided by T1 times T2, all right? And then we put the numbers in. So V1 is 0.50 liters times T2, which is 277 Kelvin, all divided by T1, which is 295 Kelvin, right? And then we do the number crunching, so 0.5 times 277 divided by 295. And according to my calculations, now in this case, I have to round up to 266. So according to my calculation, the answer will be 0.47, and the unit here would be liters, all right? Because the Kelvin units will cancel. And that's basically how that question is done, all right? Okay, any questions about this? You guys out there in Zoom, please feel free to chip in if you have any questions. Okay, there are no questions about this one. Let me clear this. And let's move on to, okay, let me see here. All right, I'm going to leave number 2 in that section for you to do. Again, it's the same equation. So you should have no problems with this one. All right, so let's move on to the next law, which talks about the Gay-Lussac's law. And basically, Gay-Lussac's law can be expressed as this: P1 over T1 is equal to P2 over T2. So this law is basically expressing the relationship between the pressure of a gas and its temperature. And I should add that, again, temperature must be expressed in Kelvin, just as in the case of the law that we saw before. So temperature must be in Kelvin, all right? Okay, so let's look at the first question here. It says, determine the pressure change when a constant volume of gas. Oh, by the way, in the case of, I forgot to mention this, in the case of the Gay-Lussac's law, the number of moles and the volume is constant, all right? So basically, that is a constraint. And I should have mentioned in the previous law, Charles' law, let me just write that down here. I'm going to erase it shortly. Where I said V1 over T1 is equal to V2 over T2. I forgot to mention that in this case, it's the number of moles and the pressure will be equal to a constant, all right? So please make a note of that. In the case of Charles' law, the number of moles and pressure is constant. In the case of the Gay-Lussac's law, the number of moles and volume is constant, all right? So let me erase this so that we can answer this question in the space provided. So the question is asking for the pressure change, right? It says that you're starting off with 1.0 atmospheres of gas, and it is heated from 20 degrees Celsius to 30 degrees Celsius, all right? So what the question is asking for is the pressure change. So the pressure change would be the difference between P2 and P1. So I'm just going to write down here, P2 minus P1 is what the question is asking for. That's the pressure change, right? So basically, what we need to do in order to answer this question, since they gave us P1 here, and they gave us T1 and T2, we need to find P2, right? But before we find P2, we need to convert the temperatures to Kelvin. So T1 will be equal to 20 plus 273, so that will be 293 Kelvin. And T2 would be 30 plus 273, which would be 303 Kelvin. All right, because remember again, the temperature must be expressed in Kelvin, right? So what we need to do we need to find P2. So based on this equation here, P2 will be equal to P1 times T2 over T1, and then we put the numbers in. So P1 is 1.00 atmospheres times T2, which is 303 Kelvin, divided by T1, which is 293 Kelvin. So let's see what that gives. 1 times 343 divided by 293. And then I got, when I did this calculation, 1.03 atmosphere, because the Kelvin units will cancel out. Now remember, we're not finished yet, because what the question is asking for is the change in pressure. As I said before, the change in pressure would be P2 minus P1, right? So the change in pressure would be P2, which is what we just calculated, 1.03 atmospheres, minus the initial pressure, which is 1.00 atmospheres, and that will be equal to 0.03 atmospheres. So this will be the final answer to the question. All right. Okay, any questions about this particular solution? Any questions? Questions? All right, let me clear this. Okay, I'm going to leave question number 2 in that section for you to attempt on your own. You should be able to do that based on what we have done. Let me see question 3. And question 3. I'm going to leave question 2 and 3 for you guys to do on your own. All right. Hold on, let me see here. This looks like a repeat. Oh no, okay. So questions 2 to 4 you should be able to do. All right. Now, let's talk about the combined gas law, because if you remember, for the 3 laws that we discussed, we have to hold 2 things constant. So let me just open this up here to explain this part quickly. So basically, we learned about Boyle's law. Boyle's law says that P1 or let me do it this way, PV is equal to a constant, right? And in this case, this is true if the number of moles and the temperature is constant, right? Charles' law says V over T is equal to a constant. And that is true if the pressure and the number of moles is constant, right? And then the third law is Gay-Lussac's law, which says that P over T is equal to a constant. And for this to be true, the volume and the number of moles of the gas would have to be constant. So this begs the question, what if the pressure and the volume and the temperature changes simultaneously, right? What will be the relationship between the two? Well, basically the relationship between the two, or between the 3, I should say, would be a combination of these 3 laws right here. So when you combine those laws, you're going to end up with PV over T is equal to a constant if the amount of gas is constant, right? Another way of expressing this is P1 V1 over T1 is equal to P2 V2 over T2. So this is called the combined gas law, right? So this law basically relates the pressure, volume, and the temperature of the gas. If all of them changes at the same time, then basically this is the equation which relates the pressure, volume, and temperature initially to the pressure, volume, and temperature at the end. All right. And of course, based on this equation, if you know 5 of these terms, then you can rearrange the equation to solve for the 6th term. All right. So this is the equation that we're going to use in the next question, which says that you have a balloon, the volume of which is 106.0 liters. They gave you the temperature and they gave you the pressure, right? And then it says, what will its volume be at 20 degrees temperature Celsius and 78 millimeters mercury, right? So just to remind you, okay, what is happening here? The equation that we're going to use here in this case is the combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. All right. So again, just like in the previous questions, we have to pay attention to the question and try to identify the terms. What is P1, what is V1, and so on, right? So the first question I'm going to ask you based on the question itself is, what is the question asking for?
V2.
V2, exactly. So V2 is what we're trying to find, right? Okay, so my next question is, what is P1 according to the question?
740 millimeters mercury.
Very good. So this will be P1. What is V1?
106 liters.
Okay, so that's V1. And then what is T1?
45 degrees Celsius, which transferred over to Kelvin.
Yeah.
273 plus 45.
So 273 plus 45 is 318 Kelvin according to my calculations. Okay, and then what is P2?
It's 7 to 80 millimeters mercury.
Exactly. And then T2 is?
20 degrees Celsius plus 273.
That's 293 Kelvin. So T2 will be equal to 293 Kelvin, right? Okay, so basically we're given, in the question, we're given the 5 values that would enable us to calculate what the question is asking for, which is V 2, all right? So basically we have to rearrange this equation here to get an expression for V2. So V2 based on this equation would be P1 V1 T2 divided by T1 P2, right? And then we put the numbers in. P1 is 740.0 millimeters mercury times V1, which is 106.0 liters, times T2, which is 293 Kelvin, all divided by T1, which is 318 Kelvin, times P2, which is, okay, what's P2? Oh, 780.0 millimeters mercury. And that's the setup right there. And let me just say, and I probably should have said this earlier, whenever you're using or whenever you're doing these problems, make sure that you include the units when you're doing your setup, right? The units will be a part of the whole process, okay? And the reason why that's important is so that you can see which units will cancel out. As you can see in this case, the millimeter mercury units will cancel out, the Kelvin units will cancel out. So the only unit remaining would be the liters unit, right? So let's see what the result would be. So that's 740 times 106 times 293, and then I'm going to divide that by 318 times 780, and then according to my calculations, how many sig figs? 3 sig figs. So according to my calculations, the answer would be 92.7 liters. Let me do this again just to make sure I put in the numbers correctly. 740 times 106 times 293 divided by 318 times 78. Oh, that should be 740. Okay, I knew I made a mistake somewhere. This should be 740. So times 740. Okay, I got 97.7. So let me raise this here. 97.7. Let me just do this one more time, just to be sure. Oh no, wait a minute. Okay, let me see here. Oh, I was right the first time. What was I? Hold on. That's P1. Okay, so I'm sorry, folks. Don't know what's going on with me and my brain today. I was right initially, because P2 is 780. So let me put this back here. Okay, let me do this one more time. I'm sorry. 740 times 106 times T2, which is 293, and then divide by 318 times 780. Okay, so 92.7 is what I got initially. So that should be correct, all right? Okay, so that's how that is done. Okay, any questions about this one? Any questions? All right, let me clear this here. Scroll down. Okay, I'm going to leave number 2 for you to do, excepting to say that in the case of number 2, it says STP here, right? Let me explain what STP means. STP stands for standard temperature and pressure, right? So basically, for standard temperature, that is equal to 273 Kelvin, all right, by definition. standard pressure, we met before, 1.00 atmospheres, right? So basically what this question is saying is that the 10.0 liters of oxygen at STP, meaning that the temperature is 273 Kelvin and the pressure is 1 atmosphere, right? So basically, those would be T1 and P1 to begin with, right? And therefore, this here would be T2, and this here would be P2, all right? Another thing I should say here is that standard temperature can also be expressed in atmospheres, which would be 760 atmospheres, all right? So 760 atmospheres is the same thing as 1 atmosphere. I'm sorry, not atmospheres, millimeters mercury, my bad. It should be 760 millimeters mercury, all right? So those are just couple of things that you need to keep in mind while trying to do that problem, all right? So I'm going to leave that for you to do. If you have any problems with any of these that I have left for you to do, please feel free to contact me. I'll be in my office today from 2 to 5, and I'll be keeping my regular office hours next week. Next week, all right? So feel free to contact me if you have any questions concerning solving any of these problems, all right? Let me see about question number 3. Let's see, question number 3. Okay, again, I'm going to leave question number 3 for you to do. You should be able to do this one as well, all right? Okay, Dalton's law. Another law, this time, this law deals with gaseous mixtures, right? All the laws that we have looked at so far, we were assuming that we're just dealing with one gas, right? But you can have a gaseous mixtures. For example, the air that we breathe is a mixture of gases, right? The major component would be nitrogen, which is just under 80%, and then you have oxygen, which is just slightly over 20%, and then you have some other gases. So Dalton's law would apply to mixtures such as the air we breathe. And it's a very simple law, nothing complicated about it. This is the law right here. The total pressure of a mixture of gases is equal to the sum of the pressure of the individual gases in the mixture, right? So for example, if you have gas 1, 2, 3, all the way to gas N in a mixture, then the total pressure of the mixture of gases would be the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 plus all the pressures of all the other gases up to and including the pressure of gas N, all right? So, to answer a question like this, it's very simple. It says that there are 3 gases in a tank, and it gives you the pressure of each gas. What is the total pressure inside the tank? That's very simple. The total pressure will be equal to 35 atmospheres in the case of oxygen, plus 5 atmospheres in the case of nitrogen, plus 25 atmospheres in the case of helium, and that's it, right? So 35 plus 5 plus 25. So according to, okay, this must be wrong. 35 plus 5 plus 25. Okay, I got 65 atmospheres, and that's it, right? So nothing too difficult about Dalton's law, all right? So that's Dalton's law. Basically, you just add up all the pressures of the gases in the mixture, and that gives you the total pressure, right? So that's number 1, and I'm going to leave number 2 for you to try on your own. Same idea. Again, if you have any problems doing that, let me know. Feel free to contact me if you have any questions about that. Let me see here. And number 3 as well. So try those on your own. So now we're going to get into the ideal gas law. Now, if you remember, I said that the combined gas law is P1, V1 is equal to T1. I'm sorry, divided by T1 is equal to P2, V2 over T2, right? That's the combined gas law. Now, the assumption here is that the number of moles of the gas is fixed, right? So this begs the question, what if the number of moles of the gas changes, right? Well, it turns out that basically, if P1, V1 over T1, I'm sorry, PV over T is going to be constant. Right? And that constant would have to take into account the amount of gas that is present, right? So it turns out that there is an equation which takes that into account. And that equation is, right down here, PV is equal to nRT. So it takes into account the N value right here, which is the amount of gas, right? So that's the relationship. This is called the ideal gas equation. Or as some former students of mine would call this, the perfect earth equation. Right? PV is equal to nRT. All right? P is the pressure, of course, V is the volume, N is the number of moles, and T is a constant, T is the temperature, I'm sorry, which is expressed in Kelvin. So this begs the question, what is R? And R is called the molar gas constant, right? And this is the value of R. R is equal to 0.0821, and please note the combination of the units. It's liters atmospheres over mole Kelvin, or Kelvin mole, doesn't really matter, all right? So that's the equation that you're going to use if the pressure of the gas, the volume of the gas, the temperature of the gas, and the number of moles of the gas is changing, right? Basically, once you plug those numbers in, then that gives you the relationship between those terms, where this is constant. That doesn't change. Everything else will change, or everything else can change. The pressure can change, the volume can change, the temperature can change, the number of moles can change, but the R value remains constant. Very important that you recognize that, right? So for example, if you look at question number 1, it says, if I have 4 moles of a gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what is the temperature? So this is the equation we're going to work with. What we're trying to find is the temperature. So if I rearrange this equation to solve for T, that would be equal to PV over nR, right? So P is, according to the question, 5.6 atmospheres. V is 12 liters divided by N. What's N? 4 moles, right? Times R, as I said before, R is always going to be 0.0821 liters atmospheres over mole Kelvin. And that's basically the setup. The atmosphere units will cancel out, the liters units will cancel out, the mole units will cancel out. So the final units you'll be left with here would be Kelvin. So let's do the number crunching. 5.6 times 12 divided by 4. 0.81. So according to my calculation, now in this case, I would have to round off my answer to 1 sig fig, and that's because of the 4 right here. So when I round off to 1 sig fig, the answer becomes 200 Kelvin. And that would be the answer to this question. All right? Okay, any questions about this one? Any questions? Any questions? Any questions out there in Zoom? You guys out there in Zoom, any questions? Going once? Going twice? Okay. Let me clear this and scroll down. Okay, let me see here. All right, so for number 2, it says I have an unknown quantity of gas at a pressure of 1.2 atmospheres. The volume is 31 liters and the temperature is 87 degrees. How many moles of the gas do I have? Okay, so it's the same equation you're going to use, but this time, so this is the equation you're going to use. PV is equal to nRT, but this time we're trying to find N. So N is equal to PV over RT, right? So P is 1.2 atmospheres multiplied by the volume, which is 31 liters, divided by R, which again, always the same, 0.0821 liters atmospheres over mole Kelvin times the temperature. Now, they gave us the temperature in Celsius, so we have to add 273 to that. So that's 87 plus 273. And according to my calculation, that works out to be equal to, take one of those. That works out to be 360 Kelvin. So that's the setup. So again, in terms of the units that will cancel out, the atmospheres will cancel out, the liters will cancel out, the kelvins will cancel out. So the only unit remaining would be mole. So we do the number crunching. 1.2 times 31 divided by 0.0821 times 360. So according to my calculation, how many sig figs? 2 sig figs. So according to my calculations, the the answer, the final answer in this case will be 1.3 moles. All right? And that's basically how the, oh, sorry, sir. Put your name on that list as well. So that's basically how that is done. All right? Any question about this one? Any questions? Any questions? Questions? Any questions? All right, so let me hear this. Let's scroll down. Okay, so again, I'm going to leave questions numbers 3 and 4 for you to do on your own, and 5 and 6. You should be able to do all those based on what we just did. All right, so do those on your own. Oh, here's a lot more. So basically all the questions in that section, right? So now we're going to get into something which is a bit more complex because we're going to combine the different laws that we learned earlier in terms of solving the problems here. You'll notice the title here is ideal gas law, Dalton's law, molar mass density, and gas stoichiometry. Now let me open this back up because I need to explain something which I already covered in the video, but I'll do this for the purpose of reminding you of what was discussed in the videos. Okay, so remember we said that the ideal gas law says that PV is equal to nRT, right? Now we can rearrange this equation here to get N is equal to PV over RT, right? Now, N is a number of moles, right? And of course, you should know by now that there's a relationship between the number of moles of a gas or of anything and the mass of the substance, right? Because it turns out that N is equal to the mass of a substance divided by its molar mass, right? So little m or lowercase m is the mass in grams, and uppercase M will be the molar mass, right? So if N is equal to this here, and N is equal to this here, that means that these two are equal to each other, right? So we can set this to be equal to this. You're going to end up with lowercase m over uppercase M is equal to PV over RT. So to solve for to solve for uppercase M, that would be equal to lowercase m times RT over P times V, right? And this equation is very useful because this equation can be used to determine the molar mass of a gas, right? So basically, to use this equation, you're going to need a couple of things. You're going to need the mass of the gas, right? You're going to need the temperature of the gas. You're going to need the pressure of the gas. And you're also going to need the volume. R, again, is constant. That doesn't change, right? So if you know these terms, if you know the mass, temperature, pressure, and volume, you plug them into that equation, and that will give you the molar mass of the gas, all right? So that's one thing. Now there's another equation that you can derive from this. Let's say you want to find the density of a gas, right? Based on this equation here. Well, let's remind ourselves of what density is. By definition, density is what? Mass over volume, right? Here we have the mass, here we have the volume, right? So if we can isolate M over V on one side and bring all the other terms on the other side, we're going to get an expression for density. So if we bring PV, if we bring P here and RT down here, we're going to get PM over RT, right? So this here is basically the equation that we can use to express or calculate the density of a gas. If you know the pressure, you know the molar mass, you know the temperature, and of course R is always going to be the same value, then just plug the numbers in and that will give you the density. All right, so I just thought it was important for me to show you this so that we can look at some of the questions here in this section. So the first question says, calculate the partial pressure and total pressure of each of the following gases in a mixture of 4.00 grams of each gas, and it gives you the formula for each gas in a 1.50 liter flask at 0 degrees Celsius. All right, so this begs the question, what equation comes to mind? Well, a couple of equations come to mind. one equation would be, I'm just gonna squeeze it right here, is the equation I just derived, B. No, not B, I'm sorry. Molar mass is equal to mRT over PV. Now, the reason why I would use this equation is that, based on the information provided, I have the mass here, 4 grams of each gas. I have the pressure, which is what, well, we don't have the pressure, we need to find pressure, but the question gives us the volume, and the question gives us the temperature, right? And we know what R is. So, and we can find the molar mass for each gas, right? So we have everything we need to calculate the pressure of each gas. So what I would do is rearrange this equation to get P is equal to mRT over uppercase MV, right? So what I'm going to do is calculate the partial pressure of each of these gases, right? Starting with CH4, which is methane. So PCH4 will be equal to the mass of methane, which is 4.00 grams, times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature. Now the temperature is 0 degrees Celsius, which is 273 Kelvin, right? And then I'll divide all of that by the molar mass of methane. So we need to calculate that. And of course, being the lazy person I am, I'm going to go to my trusty molar mass calculator. And I'm going to type in the formula for methane, which is CH4. Calculate. And it is going to be 16.04 grams per mole. So I'm going to put down here 16.04 grams per mole. And then I'm going to multiply by the volume, which is given as 1.50 liters, right? So that's basically the setup. And the units that will cancel would be the grams units there and there, the mole units here and here. Liters unit cancel out as well. The Kelvin units will cancel out. So the only unit remaining would be the atmosphere unit. So let me do the number crunching. So that's 4 times 0.0821 times 273 divided by 16.04 times 1.5. So according to my calculation, this works out to be 3.73 atmospheres, all right? So that's basically how you're going to calculate the pressure of methane, right? So I'm just going to squeeze it up here. PCH4 is equal to 3.73 atmospheres, all right? And basically you're going to do the same thing for C2H4 and C4H10. So again, because I'm lazy, what I'm going to do is I'm going to use the same numbers here, excepting that the molar mass of C2H4 will be different. So let me put C2H4 here, calculate. So the molar mass of C2H4 would be 28.05. So I'm going to put that here. So this is 28.05 grams per mole. So let me see what that gives. 4 times 0.0821 times 273 divided by 28.05 times 1.50. And according to my calculation, this works out to be equal to 230. So this will be equal to 2.13, not 230, 2.13 atmospheres, all right? And that's how that is done, all right? Okay, any question about this? Any questions? Any questions? Any questions out there in Zoom? Okay, so again, same process. This time C4H10 is the other gas. So I'm going to plug in C4H10 into this calculator here. 0. And according to this, 58.12 would be the molar mass, which I'm going to use right here. So this is going to be 58.12. 58.12 grams per mole. So let's see what that would give. So 4 times 0.0821 times 273 divided by 58.12 times 1.5. And according to my calculation, this works out to be equal to 1.03. I keep missing the decimal point. So this is going to be 1.03 atmospheres. All right. So this will be P C4H10 is equal to 1.03 atmospheres. What was the answer for PC2H4? Can somebody remind me? I forgot. The pressure that we calculated for C2H4.
C2H4 was
3.73.
3 point what? Oh,
Uh,
2.3. I remember that. I'll let you mention. All right. Okay. So what we have done so far is answer this here. Calculate the pressure, the partial pressure of each gas. And then now to find the total pressure, that's where Dalton's law comes in. All we have to do is add the pressure of methane plus the pressure of C2H4 plus the pressure of C4H10. So that will be 3.73 atmospheres plus 2.13 atmospheres plus 1.03 atmospheres. And whatever that gives, that would be the answer. So 3.73 plus 2.13 plus 1.03. So according to my calculations, this works out to be 6.89. 6.89 atmospheres. So that's basically how we do question number 1 in that section. All right. Okay, any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Okay. Ooh, time is going fast. All right. Let's clear this. Okay, I'm going to leave question number 2 for you to do. Basically, question 2A, B, and C, you'll be using this equation. Let me just write down the equation here. That is the density of a gas is equal to Pm over RT. All right. All right. So, yeah, so that is the equation you're going to use for question number 2. Let me just scroll down and see what's, let me see. All right. Yeah, so I'm going to leave question number 2 for you to do. So let's move on to question number 3 in the time that we have left. So question number 3 deals with what is called gas stoichiometry, right? Basically, stoichiometry, if you remember from before, is that area of chemistry which deals with quantitative relationships between substances involved in an equation. So if you're given a certain amount of a particular reactant, then you can find out, at least theoretically, how much product you expect to get and so on, right? Now, it turns out that when it comes to gases, if the temperature and pressure are the same for all the gases, then basically the volume ratios would mirror the mole ratio. So let me give an example. Let's say you're given, I think this was one example I covered in the lecture. Delete all this here. So let's say you have a reaction where nitrogen reacts with hydrogen to form ammonia, NH3, all right? Now to balance this, we're going to need a 2 here and a 3 here, right? And we all know how to interpret this equation. One way of interpreting this is that 1 mole of nitrogen will react with 3 moles of hydrogen to give you 2 moles of ammonia, right? Everybody knows that, right? It turns out that if the temperature, let me put this here, if the temperature and pressure of all the gases are the same, then the volume ratios will mirror the mole ratio. So what do I mean by that? So let's say, well, we know what this means already. We can also interpret this to mean 1 liter of nitrogen will react with 3 liters of hydrogen to produce 2 liters of ammonia, right? So these are all gases, right? So basically, we can do volume ratios just as though we can do mole ratios, right? And again, it doesn't matter what the volume ratios are, I should say, it doesn't matter what the volume units are. It could be liters, it could be milliliters. 1 milliliter of nitrogen will react with 3 milliliters of hydrogen to give 2 milliliters of ammonia. And it doesn't matter what the volume unit, it could be even gallons, right? It could be any volume unit, all right? So based on that fact, we can go back to this question here, which talks about acetylene, gives you the formula for acetylene. It says it undergoes combustion to produce carbon dioxide and water vapor. So the question is asking, how many liters of C2H2 are required to produce 75.0 liters of carbon dioxide? First thing I would do, as with any stoichiometric type problem, is determine the balanced equation. So the balanced equation is, in this case, determined by writing down what the reactants are, which is C2H2 gas plus oxygen, which is also a gas, and then the products will be CO2 gas and H2O gas, right? Because the question says water vapor, so H2O will be a gas. So these are all gases, right? So once we establish that as the unbalanced equation, we now need to balance it. So how do we balance it? Well, you have 2 carbons here, so we'll put the 2 here. We have 2 hydrogens here, so that's balanced already. So as far as the oxygens are concerned, we have 4 plus 1, 5 oxygens. So I'm going to put 5 over 2 here. And then what I'm going to do is multiply everything by 2. So you're going to end up with 2 C2H2 gas plus 5 O2 gas to give 4 CO2 gas plus 2 H2O gas. So that would be the balanced equation. So the question is asking how many liters of C2H2 are required to produce 75.0 liters of carbon dioxide. Then what we will do is start off with the 75.0 liters of carbon dioxide, and I'll multiply by a volume ratio, which represents the relationship between C2H2 and the carbon dioxide based on the equation. So we have a coefficient of 4 for the carbon dioxide, we have a coefficient of 2 for the acetylene. So here I'm going to put 2 liters of acetylene, and down here I'm going to put 4 liters of carbon dioxide, and then we do the calculation. So that would be 75 times 2 divided by 4. So according to my calculation, this works out to be 37.5 liters of C2H4, and that's basically how that is done, all right? Now remember, this is only true. You can only do or take this approach if the temperature and pressure of all the gases are the same. In fact, there's a law, oh gosh, I forgot the name of the law right now. But we covered it in the video, right? There's a law which says basically what I stated, that I think it's Avogadro's law of partial pressures. No, Avogadro's law, if I remember correctly, relates the volume to the number of moles, right? And it's based on this law that this is true, all right? Okay, we have 5 minutes left. I was hoping that we would get to the most difficult question. Okay, so what I'm going to do is leave questions, the B part, the C part. Okay, so, okay, I'm going to do this question. Oh gosh, okay. I'm gonna do this question in the time that we have left. Again, this is a gas, this is a stoichiometric problem. Now, in this case, let me see. Oh, okay, before we do this question, there's one thing I should mention concerning STP again. And again, this was mentioned in the videos. And it has to do with the fact that 1 mole of any gas has a volume of 22.4 liters at STP or under STP conditions, right? So this is something that we can mathematically prove, right? But for now, you can just accept this as being fact, right? 1 mole of any gas has a volume of 22.4 liters, right? Doesn't matter what the gas is. And that will be important when it comes to this question here. So in this question here, they gave you a reaction between iron and sulfuric acid. They gave you the volume of the gas under STP conditions, and the question is asking how many grams of iron 2 sulfate are produced. So the first thing I will do is write down the equation for the reaction. It's iron reacting with H2SO4, those are reactants, and the products will be hydrogen gas plus FeSO4, and we have to check to make sure the equation is balanced, which it is, right? And then now what I will do is start off with the volume of hydrogen. I'm sorry. Yes, the volume of hydrogen, which is 650 mils H2. What I would do is convert this to liters first, right? So we know that 1 liter of hydrogen will be equal to 1,000 milliliters of the same, right? So that will go with that. And then the next conversion factor will be the mole ratio between the hydrogen and the iron 3 sulfate, and that's 1 to 1. So, oh no, before we get to that, we'll get to that, but not yet, because here we're going to write down a conversion factor which represents what we just said here, right? 1 mole of any gas has a volume of 22.4 liters. So therefore, I'm going to put 22.4 liters of hydrogen down here. Up here, I'm going to put 1 mole of H2 gas, right? And then the mole ratio between iron 2 sulfate and the hydrogen will come in this conversion factor. So down here, I'm going to put 1 mole of H2, and up here, I'm going to put 1 mole of FeSO4, and then the final conversion factor would be the molar mass of FeSO4. Again, I would put here the molar mass of FeSO4, which is equal to 151.91. So that will go here, 151.91 grams of FeSO4 above over 1 mole of FeSO4 below. So let's see what that gives. Okay, so let me go here. For 650 divided by 1,000 divided by 22.4 times 151.96. And according to my calculation, this works out to be equal to 4.4 grams of FeSO4. That would be the answer for that question. All right. So that's number 4. Okay, and that's pretty much all we have time to do. So, however, for number 5, which I think is the last question, based on what we have covered previously, you should be able to do number 5. It's here. Yes, you should be able to do number 5. Okay, right. So I'm going to leave that for you to do. Now, before you leave, by way of announcement, test number 3, I've sent over to the testing center, right? In fact, I sent it yesterday. And you have from, well, it was from yesterday, but from today until December 4th, which would be next week, Thursday to do it, all right? And that test, I forgot my grade book, I made a note of my grade book. If I remember correctly, that test is based on chapters 7, 8, and 9, right? So, chapter 10 will not be on it, and this chapter here that we just completed, chapter 13, will not be in the test, right? So chapter 7, 8, and 9, is what the test will cover. And make sure, again, as I said to you the last time, make sure that the cover page of the test has this semester, which is fall 2025, so that they don't give you an incorrect test. If they give you anything incorrect, just speak up and just let them know that you know that you're supposed to do, for example, the one for fall. And make sure they give you the tables as well, because I have a student who said that they didn't get the tables. And as far as the final exam is concerned, that would be on December 9th. Now, I've decided to give you guys two options, and I'm going to put all of this in the announcement. You can come here and do the test on that day, or I can send it, and because I'm going to send the test over there anyway, I'll send it over to the testing center, and I'm going to set the dates for doing that test from December 8th to December 11th, right? And I'm doing that because I know that some students, for whatever reason, may not be able to come to the Citrus campus on December 9th, right? So if you want to come here and do the test here in this classroom on December 9th, no problem. Otherwise, I'm going to send the test to the testing center, and you will have the option of doing it there, but you have to do it from December 8th to December 11th, all right? Another thing too is that I'm setting a deadline for all late assignments. So just in case you have not turned in all your assignments for the semester, I'm going to set a deadline date for turning in any late assignments for December 7th, all right? So I'm going to set that, I'm going to also put that in your announcement section so that you have that date as a reference if you have not turned in some of your assignments to me. Make sure you email it to me as a PDF document, make sure it's done in ink, and make sure you write down your name on all the pages, all right? And I think that's all I have to say by way of announcements. So that's pretty much it, folks. Enjoy your break, and I'll see you guys. Oh, one more thing I should say here. I'm going to publish the videos for chapters 12 and 13. So let me do that now before I forget. I'm sorry, 11 and 12. So this is chapter 11. And this is chapter 12. Okay. I'm quite sure we'll be able to get through chapter 11 next class. Chapter 12, I'm not so sure. But make sure you watch those videos just in case, right? So that's another thing I need to include in the announcement. So that's, I think now I've covered everything that I need to cover by way of announcement, all right? All right, so as I was saying before, enjoy your break, and I'll see you guys next Tuesday, all right? And for you guys out there in Zoom, I'll be signing off right now. Yes, sir.
I noticed the testing center, what likely, like to call, like the sheets that you get, the tables.
Right.
What do I ask for? Because they give me like I felt like they didn't give me